Hello there guys, welcome back to another epic inexorable maths video. In this video we're looking at convergence tests once again, and we're looking at the integral test. This is the second video on the integral test. Link to the playlist and the first video in the description below. In this video we want to determine whether the sum from n equals 1 to infinity of 1 over n squared plus 1 converges or diverges. As a recap, if it converges, that means it is equal to a finite value like the number 10 or something like that. If it diverges, it's equal to infinity minus infinity, or it is undefined. So that's not good. So we want to determine whether or not it is one of those things. And again, by looking at it, maybe it's not clear. It looks like all of the terms are getting smaller and smaller and smaller. We could even write out some of them. Okay, so the first few terms here, we have that the sum of 1 over n squared plus 1 from n equals 1 to infinity. The first few terms of this, well, the first term is when n is 1, so 1 over 1 squared plus 1, that's 1 over 2. The next term would be 1 over 2 squared plus 1, so 1 over 5. The next term would be 1 over 3 squared plus 1, so 1 over 10. It's actually just 1 over all of the square numbers plus 1, and we have this here. So we're adding up infinitely many positive terms. We want to determine whether it converges or diverges. Is this equal to a finite value, or does it just go off to infinity? That's what this video is all about. So in order to do the integral test in particular, which is the test that we are doing at the moment, we need a few different conditions. The first one is that you have to be able to integrate the function 1 over n squared plus 1, or 1 over x squared plus 1, ideally. You have to be able to integrate it. If you can't integrate it, then it's not very helpful. So you need to be able to integrate it. Second of all, after a particular value of n, this thing needs to be what you call monotone decreasing, which means that after a particular value, it doesn't matter what the value is, it could be after the 100th term or after the 2 millionth term or whatever it is, from then on, it cannot get bigger ever again. It's just getting smaller, okay? The idea behind that is, imagine that you had a bunch of terms. So, you know, we have one, let's say this is, 1, 2, 3, 4, 5, 6, etc. Imagine that the first term, it has a value of, let's say, 1. Not this question, but just in general. And then the next term is actually bigger. So maybe this one has a value of 2. And then this one has a value of, let's say, 3. And then after that, it starts getting smaller, and it never, ever gets bigger ever again. You can still use the integral test on this, because all you have to do is just start from this one. So you would do your function, whatever it ends up looking like, and it depends whether you want to show that it converges or diverges. If you make it go through the top left of each one, you can just start it from here, and well, these are finite numbers. The 1 and the 2, even though it's increasing there, they're finite numbers. So it's still gonna, if you want to show that it converges or diverges or whatever, you can still do that by just ignoring the first few terms. The first finitely many terms don't affect whether a sum diverges or converges. It's only when you have infinitely many terms, if that makes sense. Anyway, that's just one condition that we need for the integral test to work. Okay, let's actually get on to answering the question. I do appreciate we want to actually start the question now, but that's a little bit of a prerequisite there. Okay, what do we do? Well, I would always do this. I would draw a graph of the function, the continuous version of the function. So 1 over n squared plus 1, I'm going to draw the graph of 1 over x squared plus 1, y equals 1 over x squared plus 1. Now, before I do this, it's not necessarily very obvious what y equals 1 over x squared plus 1 looks like. So this is what I want to draw. Maybe have a think about how you could do it. But it's not really very obvious how to draw it. But what we can do is we can just think about it a little bit. First of all, when x is 0, we have y equals 1 divided by 1. 1. Okay, so I would say maybe 1 is about here. Then do you notice that for every value of x, this thing is getting smaller? In fact, we actually know what some of them are. So it's basically just going to roughly take this shape here. And this is just for the positive values of x, obviously. It also works for the negative values of x. We don't really care about those in this question. Why did I do that then? Well, now what we can do is, and I'm also going to add in, like, here's the number 1, here's the number 2, here's the number 3, 4. Now on top of this, I am going to draw the sum. Okay, I'm going to draw rectangles that represent this, what you call a discrete sum here. I'm going to draw the rectangles in. So the first rectangle, because we're starting from n equals 1, is going to have a height of 1/2. Okay, now this is where it's a bit different to in the last video, because there's two ways. I left this out of the last video in order to simplify it, but now we're getting real a little bit. There's two ways to draw this rectangle, okay? So stay with me for a moment. I'm gonna draw this in a different color so you can really see it. So the first way that we could draw the rectangle is we could take the height of the rectangle, which is 1/2, but we could draw it in this position here. This has a height of 1/2. Or we could have drawn it over here, and this would be gone. So do you see there's two places to draw a rectangle of a height of 1/2? In one version, the rectangle is below the continuous function, 1/x²+1, and in the other case, it is above. So it depends on whether this integral, the area underneath the continuous function, if that converges or diverges, it depends how you want to position it, okay? So the best way to do this is to guess whether you think this converges or diverges. Guess. You might be wrong. That's okay if you're wrong. It doesn't really matter. But just take an educated guess. Do you think this diverges or converges? Genuinely. And you might not know. It's fine if you don't know. I'm going to estimate, I'm going to guess that it probably converges. And that's just because the terms are getting small quite quickly. But if you guessed it the other way, I'll show you what you would have done later. But let's guess that we think that this sum converges. If we think that it converges, what we should be doing is drawing these rectangles smaller than the continuous curve, right? Why? Because if we draw it bigger, then we won't be able to show that it converges, because we're going to be saying that it's bigger than something. That's useless for convergence. You've got to show it's smaller than something to show that it converges. So we should draw these rectangles taking their heights from the kind of top right-hand side, if that makes sense. So I'm going to draw the rectangles like this. The next one, when n is 2, that's you get 1/5. So the next rectangle will have a height of 1/5, okay? The next one will have a height of 1/10. And that's a very bad drawing, but you guys hopefully get the idea here. And so on and so forth, okay? I appreciate it looks a little bit messy. And then this goes on and on and on and on forever. So this is 5, whatever this is. This would be like 1/17, I think. Of course, I'm not drawing it entirely to scale, and so on and so forth. Okay, blah, blah, blah. Now, if we can show that the integral converges, we're good. We've shown that this thing converges. Now, if the integral diverges, then we need to reposition these rectangles a little bit, but other than that, it's fine. Okay, let me show you exactly what I'm talking about here. So we need to integrate the function 1/x²+1 with respect to x, and we probably want to do it from 1 to infinity, so that we can say that the area below the graph to the right of the number 1 is whatever it ends up being, hopefully a finite number if we're trying to show that it converges. And then we can say that the sum is less than that, because clearly, do you see the area of these red/pink, orange, whatever color they are, these rectangles, clearly the area of these rectangles is less than the area below this continuous curve from 1 to infinity. That's the idea. So we're going to go integral from 1 to infinity. And I'm saying here, hopefully you agree, that this integral is bigger than or equal to the sum from n equals 1 to infinity of 1/n²+1. Make sure that you're really happy with why one is bigger than the other. Okay, now the integral here, I'm not going to spend too much time on this because it's not really too crazy of an integral, but using our skills from improper integrals, this is the limit as t approaches infinity of the integral from 1 to t of 1/x²+1 dx. And I'm just going to directly integrate this. This is the limit as t approaches infinity of, and then 1 over x squared plus 1, this is a standard integral, guys. This is arctan x. Okay, arctan x. And the limits are 1 to t, 1 to t. And this is the limit as t approaches infinity of arctan t minus arctan 1, like that. So I'm just going to move out of the way. Hopefully you're happy with all of that. Now, as t approaches infinity, arctan t actually approaches pi over 2. So this is equal to pi over 2 minus, and then arctan 1 is actually pi over 4. So it's pi over 2 minus pi over 4, which is pi over 4. Okay. Now, if you're not sure why arctan of infinity is pi over 2, just remember that tan x looks like this, where this is pi over 2, and the inverse function, you flip it in the line y equals x. So the graph of arctan looks like this, where the asymptote is now at pi over 2 there. So as t goes to infinity, the value of arctan x approaches pi over 2. That's the idea, if you haven't seen that before, but hopefully you have seen that before. Just try it, by the way. If you have a calculator, just do arctan of like 1 billion and just see what you get. Okay, cool, pi over 4. So what we are saying is this integral, which is equal to pi over 4, is bigger than or equal to the sum. So in other words, the sum from n equals 1 to infinity of 1 over n squared plus 1 is less than or equal to pi over 4. Okay? Just to be really clear, that does not mean that it's equal to pi over 4. It's not equal to pi over 4, in fact. It's smaller than or equal to it. And in this specific case, it's just smaller than it. We don't know the actual value of the sum. We're not working out what the actual value of this thing is. We're just trying to see whether it is infinite or finite, and we have worked out that it is finite. It converges because it is less than pi over 4. We found an upper bound for it, so the sum converges, as we guessed, basically. Now, at the beginning of the video, or earlier on at least, I said, what if you don't know whether it converges or diverges? Or what if you guessed that it diverged? We guessed that it converged, and that's why this worked. Well, okay, here's what we can do. If you guessed that it diverged, okay, if you guessed that this sum diverged, then what you would want to be doing is showing that the sum is bigger than the integral, essentially, and then you want to show that the integral diverges, so you're saying that it's bigger than or equal to infinity. So let me just redraw this and explain exactly what I mean. So I'm just going to rub out all of these. I'm going to redraw the whole thing again, actually, just to make a clean slate here. So obviously it's the same function, so it still looks like this. But this time, we're going to position the rectangles the other way so that they're all bigger than the graph. Do you see now they're all above the graph? So now, in the way that we have phrased it here, we are saying that the sum from n equals 1 to infinity here, and again, it's still, it is still n equals 1, and this is of 1 over n squared plus 1. Even though we're starting at 2, the height of this rectangle is still when n is 1. So this is still 1/2. So it is the same sum, even though it's been moved over to the right a little bit, that's fine. But now, do you see that we're saying that this is bigger than or equal to the integral from, and now it's going to be the integral from 2 to infinity of just about half space, 1 over x squared plus 1. So we're just doing it the other way around, okay? Now, what you're going to find here is that all you're going to be saying is that this integral is bigger than or equal to a finite value. This number here is a number as well. This one would just be pi over 2 minus arctan of 2, if that makes sense. I'm not going to do all the working out for it. But this thing here, I will write down what it is. This integral would have the value pi over 2 minus arctan of 2. And all you would be able to say is that the sum is bigger than this number. However, that is useless. That is completely useless. Why does it matter that the sum is bigger than some random number? That doesn't help you. Knowing that the sum is bigger than something doesn't tell you whether it converges or diverges. You're just saying that it's bigger than a finite number. It could still converge, but just converge to a number bigger than this. So it doesn't help you at all. So you would get to this point where you go, oh, actually, that's useless. And then you go back, rephrase it, draw the rectangles the other way, and then you'll be like, oh, I see. Okay, now I actually have something sensible. So what I'm basically saying in a nutshell is, if you want to show that something converges, you have to show that it's less than a finite value, which is what we did the first time around. If you want to show that something diverges, you have to show that it's bigger than infinity, not a finite value. And here, we're showing that it's bigger than a finite value. Useless, absolutely useless. Here's an example, here's an analogy. If I said, this diverges because it's bigger than 0, you'd go, what? What? Well, that doesn't mean anything. You see what I'm saying? It doesn't mean anything that it's bigger than 0. It could still converge and be equal to like 2, right? So do you see what I'm saying? So showing that it's bigger than this, useless. So what you do is you get to this point, you go, oh, I've done it the wrong way around. And you draw the rectangles the other way, the way that we originally did it, and then everything's fine, and you can actually do something. If that doesn't make sense, don't worry, because there's other videos. So the next video, and the one after that, and the one after that, I'm gonna do more examples where we do have to do it both ways around, okay? So don't be confused, it's okay. It's a hard topic at the end of the day. So we're gonna see more examples and you'll get the hang of it. Remember guys, because it's maths, you gotta do these questions yourself as well. You do them yourself, you'll see, you'll get the hang of it. It's not an easy topic. Okay guys, as always, thank you so much for watching. I highly appreciate it, obviously, and I'll see you in the next video. Cheers.